All right, hello everyone. Welcome back to Machine Organization and Programming at the University of Wisconsin-Madison. That's Computer Science 354. I'm Mike. Today we're going to be continuing with part 2 of week 3, where we dive into two-dimensional arrays. So last time we took a look at one-dimensional arrays and their connection with pointers. We're going to be continuing that connection with pointers, looking at two-dimensional arrays. And then in the third part of this week, we'll have just a brief one more video about structures and again, how they are connected with pointers. All right, let me go ahead and talk about two-dimensional arrays just briefly, and then we'll dive into some more, like write some code, experiment with it, see how C is putting it in, storing the data in memory, and the tools we have available within C to learn about C itself. Okay, so here's the idea. I'm going to be creating, well, that's kind of cool. I get that neat shadow effect. That's clearly a glitch. I'll get that fixed. I've got 2 copies of my table there. All right, I'm creating a matrix, and that's the idea. I'm looking at two-dimensional data. This could be something like a matrix that we're using for mathematical operations, or it could be something like just a list of words, where I have an array of strings, and the strings are arrays of characters. So something like that. Both of those will see frequent applications as two-dimensional arrays in C. So an array of strings is an array of arrays of characters, or matrices. So anyway, I'm going to go write some code that builds this particular matrix right here, where I've got, in the 3 rows, 5 columns, where cell 1, 1 is actually 1, 1. Again, they're all 0 indexed, so I'm going to have to do a little bit of math. So this is actually right here, row 0, column 0, but I'm going to put these numbers in. The only reason I'm doing that instead of row 0 is because I get the 1, 1 instead of a 0, 0. It won't print 0, 0. It just rounds down to 0. It doesn't print the leading 0. And I'm neurotic and I want it to look really good, so that's what I'm doing. All right, let me go switch to right here. So I've got a template set up. This is my Welcome to C week 3 file. I'm going to be using PowerShell again because the lag was truly horrible, and it continues to be, but my kid's upstairs playing games, so it's probably on my end. We're going to be working with the two-dimensional array demo file. I renamed the one from last time to array pointer equivalence demo so that it's a little more clear what's going on in that code when I upload it. And here's the idea. I'm still going to be compiling with GCC. This is the Windows MinGW version of GCC, so it's got some differences from what we'll see from the Linux machine, and I'll point those out where appropriate. And I'm using the M32 option, so it's compiled with 32-bit addresses. So they're a little shorter, a little easier to look at, and all of the warnings. So let me go ahead and make sure this works. Run this. Yep, there it is. Welcome to week 3. All right, so I'm going to go hop back over here and real quick just print out, let's see, we're going to need that array. I called it M in the video. So, and it's going to be, I'm going to go ahead and just type this up and then I'll rewrite back. Don't need to waste your time watching me type. All right, I'm back. I've got some code that works. First of all, I'm declaring my array right here in line 10. I'm going to call the array M because I'm M for matrix. It's going to have 3 rows and 5 columns. So to declare a two-dimensional array in C, all I need to do is follow the name of my array, well, the type, the name of the array, with however many bracket pairs I need for each dimension. In this case, I'm declaring a two-dimensional array. And this tells the compiler it needs to reserve space for 15 integers. It's going to do that in just a linear sequence of memory. It's going to grab that memory and then do a bunch of complicated math to figure out which element goes with which pair of indices. All right, to initialize the array, we can just use this same row column notation with different brackets. So I've got 2 loops here. I goes from 0 to 3. J goes from 0 to 5. You know what? I hard-coded these values, and I've found myself repeatedly typing the dimensions. Let me go ahead and use some defines instead. So let's go with max row, and we'll make that 3 rows. We'll go define max column, 5 columns, and I'm just going to go ahead and use these variables in place of my 3s right there. So this first loop just initializes the matrix. The second loop just prints it out so we can see that it's working. All right, I've got a 5 right there, 5 right there, 5 right there. Okay, there we go. So it's going to loop through a double loop to get all of the cells. Now here's the formula that I'm using to put the 11, 12, 13. Basically, it's taking whatever row, so it's going to start out at 0, add 1 to it, multiply it by 10. That'll give me the first digit. So I'll have 10, 11, 12. To get that offset, to go from 10 to 11, we just need to take which column is it, J, and add 1 to it. So I as rows, J as columns. And then same deal for printing this out. I'm just using a double loop where I goes from 0 to maximum rows, J goes from 0 to max columns. We print out each of the values using the array bracket notation. And then after the first row is complete with those lines, we'll put a new line in. Then we'll go back and do the second row as the outer loop repeats. All right, let me save this. Let me jump back over here. I got it working before I put in those constants. Let's just make sure that it still works with the constants. There we go. And this is what the matrix looks like when I printed it out. I've got tabs between all of the numbers. All right, so next thing I want to do, I'm going to go back and write a little more code that tells us where each of these things are stored in memory. And then we'll go to a memory picture, the memory model, and put all of them in. So no reason for you guys to watch me type that code. I'm going to type it. You can pause the video and then type it in yourself and follow along and try your own experiments. But I'm not going to waste your time with watching me type. I'll be right back. All right, I've added just a little bit of code here, the where are all the numbers stored section. And again, just let me walk you through this. I've got a double loop, so it accesses all of the elements in my two-dimensional array. I'm using a printf statement that's going to print out the array index, so m of 1, 1. That's going to equal to, and then it's just going to grab the value. So I've got I and j going into m1 of 2 or whatever place it is in the matrix. I'm printing out the value stored there so we can keep track of 11, 12, 13, where they are. It makes this a lot more sense because I've got my picture with the cells labeled. And then right here, I'm also printing out the address in memory where these are stored. Because it's a memory address, I'm using the %p format string specifier. And this is just the address of that piece of data, so one integer. All right, I already ran this. I got it working on the second try. So here's what we're looking at. Here the matrix is being printed out, and then I'm printing out all the cells. So M00, that's the cell right here that contains the 11, found at address 61FECC. The 1, 2, just iterating straight across the row, and then second row and then third row, which is 11 through 15, 21 through 25, 31 through 35. I can see these addresses, so if we just count in hex, so we have CC, you add 4 to that, we get D0, and then 4 bytes after that is 48C, 048C, 048C, so we, D4, D8, DC. Then that increments the second digit here, so E0, E4, E8, EC, and then this turns into F, F0, F4. So they're right in order. They've given us a linear sequential block of memory and just basically unwrapped this matrix into a one-dimensional array and stored them all in order. Let me go draw a picture of this. So we got the visual, and then I'm going to start doing some experiments on it. One sec while I go prepare that and actually get these addresses copied in just right. All right, guys, I got this slide prepared. Here's what we're looking at. This is a screenshot of the data that I just collected from my matrix experiment, printing out all of the addresses where things are. You can see that the matrix starts up here at address blah, 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 ECC. So I've got my memory model where I'm starting at EC0. ECC is down here. That's where I'm storing the 11, and that's matrix element 0, 0. All right, great. I went ahead and I put in all of these. I mapped them all, and we can see now maybe a little more clearly that all of this data just gets mapped directly in memory in order. It takes the first row, then the second row, then the third row. So I've got all these addresses lined up, and just put this in a picture. All right, next thing I want to do is go through how C is actually computing the address of all of these places in memory. If you remember back to the previous lecture, I had a one-dimensional array. If I wanted element 3, then the way C approached finding that value on the inside was to actually use pointers. It would take this ARR, that's the base pointer. It's the very first address of my array. For this matrix, the very first address is going to be ECC right here where I've got M0, 0. And then it needed to shift over by 3 positions on that array, and it already knew that the size, that this was an array of integers, and so it needed to multiply by the size, or 4 bytes for this example. If we have a machine with a different number, a different size of int, then C will just take care of that for us. But I just wanted to emphasize that integers are 4 bytes here. When we do this calculation by hand and use pointer arithmetic to access array elements, we do not need the size of. C takes care of that for us. All right, so quick reminder. What I want to do is develop the same formula for multi-dimensional arrays. In this case, I'm only going to do 2-dimensional. I'm not going to go beyond that. And if you want to, we'll just extend the same idea. In fact, this is a great opportunity for you guys to just pause the video and see if you can write a similar formula for a 2-dimensional matrix. How do we get to element 1, 2? Let's see, element 1, 2 is right over here. The answer should be EE8. When we get to that's address where it's stored. The value stored is actually 2, 3. So row 1, element 2. Is that the one I wanted? Row 1, element 2, 1, 2 is 2, 3. Oh yeah, 0, 1, 2. Okay, yeah. I'm confusing myself. I've got the 1 based in the labeling and the 0 based indexing. So, yeah, all right. Row 0, row 1, column 0, column 1, column 2, 1, 2, right here. This is the number 23. That's the one. Go ahead, pause the video, write a formula, and then I'll walk through my development of it. All right. All right, guys, I'm back. Let's go ahead and take a look at the formula for getting to that memory address. All right, we're going to start with the base pointer for the matrix. Right here, we need address ECC to get started. That's the one that's actually stored. So I'm going to need the letter M right there to get that very first address. All right, next thing I'm going to need is we need to shift down by however many things are in one of these rows. We need to go and get to row 2. And the way to do that is we need to know how many columns there are. In this case, there are 5 columns. So I'm going to be, oops, what am I doing? Clicking on the wrong screen. I've got the editing screen on the right, the recording screen on the left. So I need to know that there are 5 things in each row, and I need to shift down by 1 row in this case. That 1 came from right here, the number of rows that we're shifting down. If this had been a 2, then I would have needed to shift down by 2 rows. All right, so far so good. That's going to get me to this position right here, address EE0. Now, I've only got 2 more to go. I need to get to the right column in row 2. So to do that, remember the other screen, Mike? I need to add the number 2 to this. That 2 came from right here. That's the number of columns I'm shifting over. All right, and once I've got that, this whole thing right here, that much, is what we're going to multiply by the size of an integer. And again, remember, when we do this and are typing it into C ourselves, C takes care of this multiplying by the size of an integer. So what we type in to get to a particular address, if we're using the pointer notation, we leave that out. All right, and last step, because this will get me an address. And if I want to print this out, it's going to return the hexadecimal value, blah, 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 EE8. Now, chances are that's not what I really want unless I'm testing where things are. What I really want is the value stored there. I want the 23. So in order to get that value, I need to dereference, and then everything else here is the computation of the address. So throw some parentheses around that. All right, there we go. 2-step process to get to that value. I needed to shift down by a certain number of rows. That's the 5 times 1. Then I needed to shift over by however many columns there are. Make that look a little better. All right, now I'm going to write this in more general terms real quick. If I want M, row I, column J, I'm going to have something very similar here. Let me see if I can get that lined up, looking good. So I'm going to have the base address for the matrix. I need to add to that the number of columns. And I named that max column, 5 in this case, in my example. So I'm just going to leave it like that so it matches my example. Times how many rows I'm shifting down. Okay, so I've got I rows, and there are 5 things per row. So that's going to be every time I shift down to another row, it's going to jump over everything in a row. Did it again, clicked the wrong screen. All right, and then I need to add how many elements I'm shifting over in that particular row. So that's going to be the J part right there. And then close up the parentheses around this part right here. I'm going to throw in the size of. And then last step will be to dereference this to get the value stored there. All right, I want to highlight one thing right now. Here, in fact, let me go take a look at this code. In this formula, there's a piece that's actually missing. That's something I don't need. Let me pull up the code that I was looking at a moment ago. So in this piece of code right here, everything we're doing, I've defined maximum rows, max column, so that's 1, 2. I've got a matrix. This gives me the base address. That's 3 things. To get to a particular element, I've got I and J. So that's 4 and 5. I've got 5 pieces of data that are important to getting to defining an array and using it, a matrix, a 2-dimensional array. But for the computation of a particular address, let's see, where is PowerPoint? Pull this back up. I didn't need to know the maximum number of rows. And again, C never actually checks array bounds. I can have a 1-dimensional array and access things that are well out of the bounds. Negative indices, way huge positive indices. And same thing here, what we'll find is that C has no restrictions on the number of rows. I can access row 4, row 5, row 6 with no problem, even though they're not there. It's going to give me garbage data. I might overwrite something important if I write to it, but C doesn't stop me from doing that. This computation does, however, require the maximum number of columns. So C, at some point in the code, needs to be able to go backwards and figure out, if I'm doing some sort of, right down here in this very bottom row, I'm accessing element ij as I print out everything. It needs to know how many things are in each row, how many columns there are in the matrix, in order to do that computation that I just developed to get to the right piece of data. And in this case, right here, we've defined M up here on the declaration, and it can get the maximum of columns from right there, that value. Now, the problem we run into is when we pass a pointer to a function to a 2-dimensional array. C actually loses this piece of information, how many things are in the column, if we just pass a single pointer to an array. Let me go ahead and I'm going to write a function. I'm going to write a function actually that prints out, how about all of this stuff? How about just this piece? We'll keep it small. And then we'll pass the matrix to it, and I can demonstrate what goes wrong and the error messages we get. Good stuff. Actually, this isn't that hard. Let me just walk through. It's just a bunch of copying and pasting. I think there's some value in just like taking a look at what I'm doing. So the first thing I'm going to do is I'm going to put a space between the old work and the new work. And then I'm going to just call a function. We'll call it print matrix. And I need to give it the matrix that I'll be printing, just M in this case. M is it's a 2-dimensional array that's more or less the same thing as a pointer to that base address. So then I need to go write this function. I can see that it's a void function. It's not returning any value, and it takes that matrix as a parameter. So I'm going to go ahead up here, write the prototype first. It's a void function. Whoops. Print matrix. There we go. And this is an integer array called M. I'm going to keep it M so I can just copy and paste that text. So I'm going to do the prototype right here. This has max rows and max columns. And for now, I'm just going to put in as much detail as I can. Some of this is optional, and screwing some of it up is really bad. So I'm just going to put it all in for right now. And now I'm going to write my function definition down here at the bottom. I did everything at the top in the previous lecture, so I figured I would break this out into prototype and function definition. This is the definition. This is the declaration or prototype. Did I spell that right? Yeah, that looks pretty good. All right, so I've got these signatures, they need to match. So this signature right there absolutely must match what's up here. All right, next thing, all I want to do is print out the matrix. I've got code for that right here. Print the, let's call it a matrix. Initialize the matrix. declare the matrix. That's just keyword for me that says it's two-dimensional. All right, the next thing, let's go ahead and just like, this is where the print matrix function is actually starting, and it has an underscore in it. All right, let's go ahead and just verify that this is working. So I'm going to save this, jump back over to PowerShell in this case. We'll compile it, and let's see. Now it looks like I made a mistake. In function, two-dimensional warning, implicit declaration of print. Did I mean printf? Okay, so somewhere I've messed up. I have a print when I mean, there it is right there, printf. All right, try this again. There we go. No warnings, no errors. Let's go ahead and run this. And now I can see that my print matrix function, it's actually printing this out just fine. No problems. All right, so next up, I just want to do a little experimenting. So in the computation of our address, we learned that we only really needed I, J, M, and the max columns. We did not require this max row number. I'm just going to take it out. Okay, so I'm passing a matrix where I'm not giving C all the information it needs. And I want to highlight one more thing. I've got M here twice. This was a question that came up on Piazza about just the one-dimensional arrays when we call functions. So we've got actually two different M's right here. And maybe this would be better with a different variable. In fact, let me change that just to highlight the difference. In my main function, I have a variable M that's essentially a constant pointer to the very first starting address of that matrix. I'm going to change this here. Let's call this mat inside of the function. So let's see here, I, J, here's the only place I'm using it. This is now going to be a pointer inside of this function. So in the function call, it's going to add an activation record or a stack frame. They mean the same thing. They're synonyms. This is going to be a pointer that holds the address of this matrix right here, M. So this is actually different. This is a local, a parameter to the function. All right, let me go ahead and, so I took that out there. I left it in up here. So that's my first experiment. I'm going to see what happens when the prototypes don't exactly match. We'll run that. No problem. In fact, C completely ignores whatever is in this first parameter. It doesn't care how many rows there are in your matrix. It doesn't need that, and it's faster if it doesn't have to keep track. So it doesn't. It just completely ignores whatever is in the first bracket. It does need the information, how many columns there are, how many items are in a row, in order to compute like the values at indices beyond the first row. All right, so we do need that information. Let me go ahead and just run this to make sure it still looks good. Still looks good. All right, next thing I want to do, next experiment is what if they don't match? So right now max columns is set to 5. Real quick, let me change this to 3. All right. Oh, and I can take this out. Max row is absolutely not required. And let's just take a look at this is going to generate an error message. But I think learning about this is valuable. We can see a little bit about what's going on. So here we go. Warning, passing argument of print matrix from incompatible pointer type. So print matrix M, it knows that this is a matrix that has 5 values per row. I want to highlight too that this is a warning. This is just, it'll let us do it, no problem. But the function is expecting 3 things in the matrix. Okay, and this is my function prototype. So it's going from top down. First thing it does, records the prototype and knows that I should expect matrices with 3 elements. We get to right here where we print it out, and it finds that this doesn't match. M is a matrix with, in this case, 5 elements. So that's where that warning came from. It's not going to stop me. And then, all right, the next thing in red right there, bold red, is the error message. Conflicting types for print matrix. So as it continued to go through the code, it finally reached the definition and found that this did not match the prototype. That's where the error is coming from. Those two absolutely must match, the declaration and the prototype. So I'm going to go ahead and change the prototype so it matches. I'm still going to be using incorrect dimensions here because this is a great experiment and really does a lot to highlight exactly what the machine is doing on the inside. All right, so I've changed this value. I need to save this. And now we'll go ahead and compile this again. This should still give me that warning. Let's see here. Yep, compile. Right there, here's the warning. I'm going to highlight that. That's what I'm looking at. Incompatible pointer type. This is the one that's telling me that the function expects a matrix with dimension 3, but I'm giving it a matrix with dimension 5. But it's not going to stop me from letting me do this. And in fact, I think if I remove all the warnings, oh, it still gives me that warning. This is a big one. Okay, so I'm going to put warnings back on. My Mountain Dew got in the way and I mistyped there. Alright, so now we need to run this and see what it's doing again. Alright, so here's the original matrix. This is the one in main up at the top right there. Here's where everything is located. And then in the print matrix function that I messed up, I changed things. It's now printing the matrix. Alright, what I want you guys to do, this is a brain twisting experiment. And when you figure it out, it will really solidify for you that you understand how that address computation is working. But pause the video, stare at this. Here's the problem right here. This value is 14. It's supposed to be 21. This value is 15. It's supposed to be 22. This value is 21. It's supposed to be 23. Okay? Just check this out. The first row works fine. So this is one of those places where if you mess something like this up, it might work some of the time. First row is good. The rest of these values from the first row and beyond, all the values are wrong. They're being grabbed from the wrong place. All right, so pause the video, give this some thought, think about what's really happening here, and I'll be right back to explain this. All right, I'm back. I added one more line to this code so that I could use my formula here without having to switch back and forth between PowerPoint and this screen right here, the output screen. So what's happening here? Row 1 works just fine. It's computing the address starting with M. That's going to give me this base address right here, the FECC address. And then to get like everything in row 1, the I value here is going to be 0. 0 times anything is going to be 0. So we add J to it, and that'll give me the J is 0, gives me this first entry. J1 will give me the second entry. J2, 3, 4. Then we get to 5, that's the end of the row. Okay, so we got a new line that prints out. And then when it's computing the second row, we're getting a 14 here. This is the incorrect number. What we've done is we've started with the base address, FECC, and we're incrementing by I times the number of columns. Now, I didn't put max column here. That would be 5. I've got that defined in there. Instead, what it's using is the value that I passed to the function. In that case, that was a 3. So when I is 1, multiply that by 3. The very first entry here will be J0. So instead of shifting over by the entire first row, we've only shifted by 3 things. So we start at 11, we go 1, 2, 3, and we ended up at position 14 in that matrix because I have the wrong number of things in each column. And that's where the 14 is coming from. It's because this column that we use to tell the matrix that this is a row, only got 3 things per row, is wrong. So that's what's going on right here. So if this address computation made sense to you guys, this formula, the error is right there, and that came about because of this number right here, the mistake that I made. This is like a really good reason that we should always use these defines for dimensions of all matrices. Very common in C to use something like this. And in fact, I'm going to go ahead and just change these back right now. If you guys have any doubts whatsoever, what I'd like you to do is do an experiment. Change max columns to something else. And give this a try and just see if you can compute the address and figure out what you should be getting if you make a different change. Make a prediction and just verify that your address computation matches up with what you think you're getting. Okay. Yeah, that's going to end this section. I also want to do one more thing right here. So right now I'm declaring the matrix. I'm going to just print out a bunch of stuff, one in the function and one outside the function. So right here I'm printing my matrix. There we go, that's the entire matrix being printed. and where all the numbers are stored. I also want to print out just where M is located. M is at address, and then you need an address, %p, and this is going to be, let's just print M. That should give me the address. Yeah, that looks good. And then inside my function, I'm going to go ahead and put mat inside the function is stored at this location. Save that and compile. Yep, I fixed all the mistakes, so we're no longer getting that message. We run this, the matrix is back to normal. All right, and again, here's what's going on. Inside of main, I've got M. This is my matrix. It's essentially a constant pointer to the very first element of the matrix. Excuse me, FECC. And then when I go ahead and look inside the function, oops, look what I did. I printed the wrong thing. Let me go back to the code and show you what my mistake is. So what I'm doing here is printing out mat. This is a pointer. Right here, this is a pointer. Array notation, but it's still a pointer. I'll change that in a second and show you another way to declare these arrays. But I'm printing out the value stored in that address, not the actual address. So mat equals %p, and it's at address. I need the address of mat. Okay, that's what I really want. And in fact, let me go change this line up here where I'm doing the same thing for M, but we'll change this to M because mat does not exist outside of the function. And we'll make the grammar look a little better. All right, save that. Compile, run. Okay, is it better? Much better, much better. Okay, excellent. So M is a constant pointer, and when I do the address of, it actually gives me this FECC. So it's not a pointer that's been given its own memory address and points to the start of the array. The compiler, when it uses that symbol table during the compiling process, just assigns the location of M, where it would be stored as the first element. And that gives us everything we need for the compiler. And then as soon as we're done compiling, it's done. It's been replaced, this address of mat, or address of M, with this binary number or hexadecimal number for the address in every place. Now, when we call the function, we're actually passing this address. In fact, in the code right here where I call print M, I'm giving it M. And I printed out M right here. It's giving it an address. And that's assigning this address to the pointer. Whoops, I missed. I should be highlighting that one. Passing that address to mat. And that's why the value of mat is the same address as the starting value right here. However, mat is actually stored at a completely different address, FEA0. So check this out. A0 is way above all of this stuff. The very first element is FECC. A comes before E. So this is going to be much higher in memory. And when I've my stack frame for main is at the very bottom of that array. It's at very high addresses. When I add another function, and I've got to have a bunch of things. I need the return value. This one doesn't have one. It needs a return address. It needs to know where the next stack frame is located, the base pointer. It needs to know the parameters. And in fact, we've declared a new parameter for holding mat. So this is one of the things that came up in Piazza about the homework assignment, in that you're converting binary numbers to decimal numbers to binary, hex to decimal to hex. And I've got arrays stored in main. And when you pass those to the functions, if you make changes to where the pointers in the functions are, for example, if you declare your own array, do the computation, and then reassign that pointer, you're reassigning a local variable to a new location. Basically, you're changing this number, and it no longer points to the matrix outside, the matrix in main. So this is essentially a way to do call by reference, but everything is call by value. We're just passing the value of a pointer. So it's a little deceptive and can be one of those things that trip you up. I just wanted to take a minute and talk about that because it did come up with the homework. All right, that'll almost do it for me. I just took a look at my notes, and found one more thing I'm missing. If I'm trying to print a matrix of words, a matrix of strings instead, what that's going to look like, it's going to be a character array, matrix of strings. I need the pointer here, or I can make this an array. In this case, I'll have rows, I'll have columns, and I'll have number of characters. Let me try and make this look a little better, like real variables. I'm not actually going to do this as an example, but I just wanted to highlight one thing. So I will create an array that's got 3 dimensions in this case, multidimensional. And if I have a function, print matrix of string, something like this, we'll give it this variable as we pass it in. And then the prototype and the function declaration, when I do this, I can make it look good. Functions start with capital letters. It doesn't return anything, so this will be a void function, and it requires my variable. I need to know the type, so it's going to be a character, matrix of strings. When I type this in, I need, whoops, missed. I'm trying to talk and type at the same time. Whoops, not working so good for me today. I don't need the number of rows. C doesn't care about the first dimension, but in order to compute a particular character's position, figure out where it is, I need to know how many columns there are, how many words I have across the first row of the matrix, so it can jump down. And I need to know how many characters are in each of these things. That's true for any multidimensional array. This is the one that's optional. I don't need the very first dimension, but I do require how many things are in every other dimension. So I just wanted to mention that. I'm just going to leave this stuff right here in my file as a note. And if you guys like, this is a place where I would encourage you to set up your own experiment and try just a 3-dimensional matrix example on your own. It works the same way. We're just adding one more piece of information to this computation. All right, that's going to do it for this video. I'm going to go grab some lunch, and I'll be back after lunch with the final part for this week. Have a great day.